All right, I am excited about this particular BrainCandy. This is one where I've been working on this for a little bit. It's a recommendation from someone from one of the comments left on a different BrainCandy. And I want to try and explain a little bit about why we see some of the different results that we see from AI. And if you go back to the basic laws of how we've set up information, how we store information, and how we process a number of these different things, you can see there's some causal relationships down there in terms of how things are actually showing up and where we may be artificially confident about very wrong things. So if you've ever asked a question of any one of the bots and gotten back a perfectly grammatical, completely wrong answer, well formed, appears to be well thought out, but absolutely wrong. There was a number of different incidents of this where people were posting this. You saw it on Reddit, you saw it on Google, you saw all these other different things. It became a meme around asking different questions where it would authoritatively pull information that came from answers that were off of Reddit and were horribly wrong, often sarcastic, as if it was the truth. Well, there's a reason why things like that happen. It's not necessarily that it's a bug. It is actually part of a feature, and I think if we think about it like that in terms of it's not a bug, but that is a feature of how it's designed. That is the story of AI in 2026. And it doesn't mean that it's going to stay like that forever. There's things that we can do, and there's ways that we can move things forward, and that's really what this episode is all about. So I'll cue up the question here on the what if the deepest limit of AI is that we taught it information, but we have not taught it meaning. Humans live in meaning. Information is just data. So I want to introduce Claude Shannon, and there is lore in Anthropic that, and it's been even reported in the New Yorker that Claude is named after Claude Shannon. It's depends on who you talk to, whether it's just lore or whether it's partly true or whether it's something unofficial versus an actual name. They were just going for something friendly and approachable as a name, and it turns out it's pretty easy. You can talk to it as if it were Claude. The Regardless of that, whether you are dealing with LLMs or agents or RAG enabled systems, it's actually going to be pretty causal as we go through this to say, okay, well, this is a link that makes sense, and it's sort of the Claude before Claude, certainly whichever Claude it is that you're talking about. Now, AI is built on information, and humans live in meaning. As I said at the start page, it's just 8 simple words, but it has a lot of layers to it. Because as we go through here, every time that you get a confidently wrong answer, every hallucination that you see, it will trace back to this is the way that information is stacked, not necessarily the meaning that we layer on top of these different things. I'm going to talk about 2 men, Claude Shannon, Warren Weaver, both absolute geniuses working through many different problem spaces and uh, responsible for words that we use today that are affecting our society, even though much of the things that I'm going to talk about today happened in the 1940s. So Claude Shannon, he built the math that drives communication that we have today. Lots of great and brilliant things that around how that came through. And he's a very interesting guy, and we'll talk a little bit about that. Warren Weaver, not to be left out, he is one who tried to bridge some of the math to bring in language, and he did this with many different bright ideas. He put them together, and if you squint a little bit here, you can see these 2 different images kind of spoil the rest of the storyline. But if there's interest, I'll figure out a way to be able to start to post and share some of these with a deeper level of introspection where you can inspect what's going on. So the patron saint of serious play. I, I chose this as a for a reason. When we talk about Claude Shannon, we're going to talk about him first. He's in a serious place. Bell Labs, building different things that really matter in the not just then, but in the future. So if we think about his origin story and you go back to when he started, it's almost a little bit too on the nose. He is a small town Michigan kid. He built a telegraph over a barbed wire fence so that he could talk to his friend who lived a half a mile away. That is not something that every child did or does, and the desire to just know how things work. That's what drove him. When somebody asked, "Is like why do you do this?" It was not because he's trying for fame, not because he's trying to build an empire, just because he wanted to know. He had that insatiable itch. I think he and I would get along well. He goes off to Michigan. It's a dual degree in math and electrical engineering. And even in college, the things that mattered about him, he loved abstract symbolic logic, not necessarily a love that everyone has. He also loved hardware. Hardware is becoming even more popular now and more important now with the advent of AI. How do we actually turn some of these different things? And I heard someone say once that software is just for the things that you can't do in hardware in a sustainable and scalable way. So hardware is always going to be faster. But his whole career is really about where these different things meet. Go figure, he's at the forefront of computing as it's starting. Well, one of the biggest things that he contributed is he put math on top of circuit theory. So circuits are when you got a relay and it's connecting and it's disconnecting. He said inside of his thesis that this you could just prove this out using actual math and symbols, so true and false, and this is the foundation of all computing. It is the foundation of telephones. It's the foundation of networks. It's all just Boolean algebra, all ones and zeros, all trues and false. And so he took hardware and turned it into a mathematical representation, which allows a lot more research and things to be able to bring the whole field forward in a much more meaningful way. So he spent time at Bell Labs, and to call Bell Labs the Florence of its age, the digital renaissance, is not actually very going too far. And I know sometimes you talk about some of these things and it's the proliferation of pros, but so many things that we use today, from the mouse to screens, the way we interact with computers, so much started off in Bell Labs. And he spent wartime working on cryptography. He kept the wartime communications unbreakable. That was the goal. He even had lunch with Alan Turing, another amazing mind, and he was over in the UK building out some of the first computers as well. And while this particular paper looks fairly modest, you can still buy a copy, by the way. While I was looking for images to be able to plop in here, I found that you could still get a copy for $9,500. But the mathematical theory of communication, and without exaggeration, this is a founding document of the digital world. You don't have to read the whole thing. You can read just the first few pages, and you'll start to understand why it really was important. If you do read those first few pages, you'll see something in there that is absolutely true, but also part of why we have the systems that operate the way that they do today. So I'm going to actually read this piece because it's brilliant, and it also is causal for a lot of what we're talking about. The semantic aspects of communications are irrelevant to the engineering problem. That simple statement has a lot of weight to it. There's a lot of layers in there. What that basically means is that he didn't care what it meant. And when you're thinking about like a telephone call, you don't care whether it is a love note, whether it's two teenagers expressing their love for one another, or whether you're talking to your grandma or placing an order for food, or whether it's NASA getting a information from astronauts who are posted up on the moon. Communication is universal, and getting the information from point A to point B is the goal. And so that simplification is part of what allowed him to be able to create the math that allowed a lot of the current sets of systems to be able to scale out. So within that one paper, he defined words that we still use today. So everybody's heard of bits and bytes and all these different things when we're talking about computing. He's the guy who came up with the term bits. He literally invented it, a binary digit. So he also gives us entropy. Not that entropy was a new thing that he didn't coin, but how to use it within system design, and what it actually measures is a source of unpredictability. So how much is going to actually happen as it goes through that different line? And it gives us channel capacity. How much of our time is spent talking about bandwidth? Do I have the bandwidth to be able to stream 3 Netflix movies into different portions of the house and be able to run everybody's phones and to be able to all the things that we do today that we take for granted as digital come down to the bandwidth that was enabled by the design that he laid out here. And then how you code things. So coding and decoding, a codec is what's used for things just like this particular video that you're watching right now. If you're watching this on YouTube, or if you're listening to it even just on your phone, it's codifying that information so that it can compress it, send the message despite the entropy, still get it to the other side with that noise, and then be able to decode it and show it on the to what it is that you want to be able to see. So from Wi-Fi to space communications, all those types of things were built based upon this set of fundamentals. So a few words on entropy. Entropy is often talked about like it's chaos, right? But it's not. It's a more complicated and nuanced thing when you're talking about math and trying to put these different pieces together. So simple gut check and mental exercise for everybody here. So we're going to imagine we have 2 different bags of marbles, one which is full of orange marbles and another one which is full of 10 different evenly numbered sets of colors of marbles. And you pull out a marble from the orange bag and you get a orange marble. Anyone surprised by this? No. If you pull out a marble from the other bag, you have a good chance of being surprised. You may make a guess, but you got a 1 in 10 chance, and that's still not a lack of surprise. That's just that you made a lucky guess. So he introduced this concept to be able to say how informative it would be to know how much things could go wrong within the span of what it is that you're sending. So this actually is it hooks into AI, even the way that we're talking. And I'm going to get a little bit deeper into this piece as we go along. But basically, it's saying we want to be less surprised by what's going in and what's coming out. We want a little less entropy as it goes through that line. The goal is to be able to do it as cleanly as possible, to be able to give that answer. If you think about that, that should be resonating in your head about, hey, I wonder if that's causal to the answers that we get now, because we're trying to lower that entropy, the surprise in what the answers were. Before I go forward on a little bit deeper into that part, though, I wanted to talk about what a delight he is. So this is not necessarily covered in all the different history books or the science books or the math books, but by every account that I can find, he was a delight. It was a trip. He rode a unicycle through Bell Labs himself, often while juggling. He built a chess playing machine. He built a flame throwing trumpet, which is an interesting choice. And I think one that is kind of fun. He built the ultimate machine. The ultimate machine is one where you turn it on and it turns itself off. I actually knew somebody who had one of these things. I had no idea that he was the guy who originally built it. And then being able to, he built a mouse that would learn through trial and error the way through a maze and then would remember it. You don't have to. Theseus, this particular mouse, harkens to AI of today. If you want to talk about one of the early forebears, we're absolutely coming back to this. Oh, by the way, he also signed the birth certificate of AI. So there was a lot of conversation around this as computing was coming together. And they're like, hey, we think that if we get a group of really smart people together, we could solve this artificial intelligence thing like in a week. Well, maybe that was a little bit aggressive. It took a couple decades, but that proposal is what gave the field its name. He's one of the founding fathers who signed his John Hancock on that one, or his Claude Shannon on that, along with Marvin Minsky. A lot of people now know that name, John McCarthy and Nathaniel Rochester. So this particular memo was not just adjacent to the birth of AI, it's at the table. It's a contributing fact. So, what is the model? So, with the math, he laid out this model, and it seems pretty simple, right? Here's just a little flow diagram: source, encoder, channel, noise, decoder, destination. All right, that seems pretty straightforward when you break it down. So he put these different things in here to be able to help inform how messages go from point A to point B. And for us to then be able to do math within any one of those different blocks, to be able to predict it, to be able to explain it, to be able to take that forward. Now, the real amazing bit about this is that it works for anything that moves information. It moves for not just, hey, we're trying to send an encrypted message from point A to point B, but anything else. And I'm going to go through a number of these different ones. So one, let's think about the telephone. This is what he was originally building this for, right? This was the 1948 use case. A phone call, source, you. Encoder, microphone in the phone. Channel, copper wire going across the country. Noise, every transformer, every hop, every hum, every bit of electricity, all the solar flares, whatever, electric strikes, lightning strikes, every neighborhood, every neighbor's razor, all that type of stuff causes noise as it's going through there. And then it hits the decoder, the earpiece, the bit on there, and then the destination is your mom. You're calling your grandmother, whatever. Same model all the way through, does the math, allows you to be able to explain these different things. The internet. You might have heard of that thing. If you're watching this or listening to me, it's chances are that's how you got to this. But a web app like the one that YouTube runs, the protocol stack, TCP/IP, all the how do we gonna pull this apart, put it back together, and then over fiber down to your house, to your phone, over the wireless. You get packet loss, you get congestion, you get all the different things that go along there. You get little bits that drop out. And how does it still get reestablished on the other side? Maybe you see a little bit of pixelation on the monster, but my voice still stays clear. Now you know you're still got, these are reasons why some of these things happen the way that they do. And then you get that receiving stack and boom, out it comes on your browser, on your phone, on the different devices that you're listening to. And then for people, right? Just how do we communicate with one another? This is where I think it gets a little bit fuzzy, but I wanted to point it out because I think this is the bit that maybe we've got a trick in. My brain, I'm talking to you. My mouth, my tongue are sending. That's the encoder. The channel, the noise, all the internet, all the air. This is the second time I've had to record this because there was a storm. It was so loud. My dogs were barking. It was insane. That one did not work. So this is a little bit better today. And then you got to go through the decoder. You got to be able to get to your ears out and then into your brain. Are you hearing what it is that I'm sending out? Mostly that works, right? I like to think I'm a good explainer. I've been told I'm a good explainer. You're hopefully a good listener. And between us, maybe we can get that message across. But it's never that simple, is it? So this is one of my favorite stupid word jokes. And it's so true here. When someone says, let's eat grandma, we assume they put a comma in because one is family time and the other is a felony. And so the only difference between those is a comma. And if we think about this, this is basically the same number of bits. It's the same basic set of information. We assume a lot inside of that message. We assume we know which one we meant. We very, very infrequently do. We actually eat our grandmothers. And he genuinely threw that bit of information out because it wasn't that important. When someone is talking on the phone across the country, one to another, you can assume that they're going to put those different pieces in there. They're going to put in trust and context and intention. They're going to take that stuff for granted, whether you're standing in a kitchen and dealing with noise or whether you're watching a horror movie in a movie theater. It doesn't matter. You're going to still build in things based upon your human experience that not just because this is funny, but help you to actually make sense of the world around you. So all that said, this is not to poo-poo what it is that he said, and thus my little army of monsters here cheering. But it does nail a number of different things. Right? It doesn't cover truth. So the internet, radio, other things have been used for spreading non-truths just as much as anything else. Right? The world panicked at once when a radio show was about aliens landing on the planet, because they thought it was true, but it was not. Not to mention anything that people are doing with social media these days. Compression, what gets squeezed out, how bite-sized different things. Like today's problem with that is, here's this full white paper. Please read this for me, AI, and give me the 2-paragraph sentence. I think you're gonna lose some stuff. Noise tolerance. How much noise is okay? Yesterday's thunder and lightning and boom, big storms, not okay. Occasional dog bark, all right. Capacity limits, how much can go through there? Cryptography, error correction, all those types of things. He didn't take that stuff into account because he didn't need to. But he did get reliable transmission. He did get all the different, every codec that we use today is based upon this. All of the things that we send, whether videos you watch or audibles you listen to, or any of those different things. He engineered and opened the door to using symbols and math, a whole wave of innovation. We definitely deserve some praise and some love. Now, it doesn't have those different things that I just talked about, like truth, intention. It doesn't have context. You can't, trust is not included. It's not in the math, right? The effect, did it actually change any of the different things on the other side? Did my favorite example of this is in any organization of any sufficient size, you just actually one person to another person. You say, okay, these are the goals. This is why we want to achieve what it is that we want to achieve. And people interpret that. The easiest example of this is that telephone game that we all played when we were young, saying, okay, I'm going to whisper this in your ear, and then you're going to whisper this in somebody else's ear. By the time it gets to that fifth person, it is a different message. You have maybe the core of some of the words that were around there, the things that were obvious, but you don't have the other pieces. It doesn't take into account these different types of things. So meaning in the message is not necessarily included. Very important note. And part of the key as to why we see some of the behaviors that we see. Be beautiful, perfectly encoded inside of a model. That's why you get that perfectly, beautifully encoded false sentence. And again, this is what an LLM does when it hallucinates. So, but somebody else saw this gap in 1949, and he did something about it, or he tried to do something about it. Warren Weaver. So Warren worked at the Rockefeller Foundation, and I'm going to refer to him as the patron saint of taking great ideas and turning them into other fields and making them matter. So he was a working mathematician. His real superpower within the Rockefeller Foundation was making connections and bringing together other different folks. He's the guy who actually coined the term molecular biology. This is something which is having an impact on our lives today. It affects healthcare. He coined that back in 1938. And he helped build the lab that now has given us the structure of DNA that is enabling so much more innovation. And back in 1949, when he saw this intimidating math paper, years before it became a book, he said, you know what, we can do something about this. And he wrote an essay on this and said, this is what we should be able to do. What if it's not just about the wires? What if we could do some other different thing? So he introduced 3 levels of communication. Start at the bottom. A, did the symbols arrive? That's what Shannon's all about, right? The technical problem. Did we get it across? Is it correct? All the things that we just covered. He also introduced B, meaning. All right, this is the semantic problem. Is it understood? Do we have the right pieces to be able to put this together to be able to get a good answer? Let's eat grandma. Let's eat grandma. These are the things that matter. And then C, it's the effectiveness problem. Okay, great. The message arrived. Did it actually do anything? Does it result in the thing that you actually want? As we get into agents and agency, this matters a lot. This is going to be not a someday problem. This is a now problem, right? He knew it was going to be a someday problem. It is a now problem. First, I have to call out the fact that this is just a recreation of the image on the other side of the note that he wrote. I asked for one from ChatGPT, and it was so good I felt I should put a stamp on it that said recreation. So he wrote this memo, and it's now famous. He sent it to like 30 people, but it's now gone all around the world. He basically invents the idea of computer translation. He asks, what if Russian is just English but written differently? Which is a brilliant thing that we kind of sort of take for granted now, that hey, input in one language is just language and I can translate from one thing to another. But it was a novel idea that hey, we could just use computers and information theory to be able to take some of the ideas that were there in cryptography to be able to crack that and to be able to do it. So he was not wrong about the ability to be able to take that, right? So he might have picked a poor analogy of specific pieces, but the translation isn't, it's not just a single cipher. There's a number of different things. But he set the agenda, and the statistical machines that followed, LLMs, every LLM, modern LLM based translations. It's just a large language model. It's mapping things into concepts, mapping things from one into another. Every single one is descendant of this memo. So he is, in a very real sense, the great grandfather of ChatGPT, certainly of translating your emails. So we've now done the history, and I'm going to go into, well, what does that mean for AI? What does that mean for now? What does that mean for 2026? And for the things that are going to happen in the future in 27 through 2030? It gets a little both miraculous and kind of deeply weird. So an LLM in Shannon's language, right? So we'll take that same source encoder piece. Hopefully you're getting familiar with this diagram by now. You put in a prompt. It gets tokenized, goes through the context window. Within that context window, it takes it and breaks it down and figures out what's going on. It does next token prediction, and then it gets back to you with an answer to say, okay, this is what I think based upon what it is that I have. You give it that prompt, and away it goes. It says what comes next. It uses concepts like cross entropy to be able to give you a regular thing. This is a formal mathematical description about how, and the goal within the models is to not be surprised with the prediction and to give an answer that does make sense. LLM training has gotten very good. It's got very good at not being surprised. This is why we see some of the things that we do. Now, this is where one of the laziest takes on LLMs. It's just autocomplete. It's only half right. There's more to it in this training game than just next token prediction. I think Shannon would have recognized this particular set of math instantly when he took a look at it. But here's the bit that people miss. When you do predict the next token over the entire written output of humanity, something happens. When you hit that scale, capabilities that the game of token prediction never predicted emerge, right? So when you hear emergent behavior, this is what we're talking about, whether that's code generation or whether that's abstraction into other sorts of predictions, or whether that's general competence in terms of being able to create a PowerPoint slide or an image that makes sense. All of these sorts of things are emergent behavior. It is very different than just autocomplete on steroids. So while technically true, it is existentially incomplete, right? It's akin to saying, well, the human brain is just neurons firing. And while that's true, it's also not really true at the same time. So lots to think about and to pull apart inside of there. Now, I think this is important for people to understand. Hallucinations are not noise, right? It's not an error that's happening inside of the system. I know that sounds weird because you're getting an output that's wrong. How is that not an error? It's not noise like when the lightning hits a line and you get corruption and you hear static. That's an error, right? That's a problem. It is perfectly fluent. It makes sense on the diagram. These are absolutely made up words, but it looks right. The model wasn't corrupted. It's just the signal actually arrived perfectly intact. It removed the entropy from that system. And so by doing that, it never really achieved the meaning. So the bit that comes out from underneath it. So this is why you can't just fix hallucination by upgrading your fiber optic cable, getting more bandwidth, getting a better, less entropy inducing line. That's just not how it works. You have to fix it at Weaver's level B. All right, so you have to go into the system itself. You got to work on the grounding, the data that goes in, the training, and the ecosystem around it. So this is where RAG starts to come in, right? So why is RAG a thing? RAG helps at the encoder level. the bit I want you to take away from this is to think about RAG as kind of better luggage for facts, right? There's all this training data. It's all within there, within the system. It brings all that different data together. It makes the model overall capable of a certain set of things. And it doesn't make the model smarter when you put in RAG. It just is giving it better sets of local context information. So you can say, here's a set of facts, right? I have a bald head, I have a long beard, I have whatever. Don't give me a generic answer for a generic guy when you're trying to build out different images that would have me in it. These are the types of things that you would include, or whether it's your company and you're looking at your SharePoint sites and your other financial filings, or whatever the different bits are that you're including. It's a set of bags and luggage that you can attach and then feed through to be able to make sure that your next token predictions are going better. Now, it is important to note that when you are talking with this, if you ever wondered why on prompt the folks on Twitter or X or on YouTube are sound like they're describing a cult when they're talking about prompt engineering, it's not that they're actually describing your prompt. What they're doing is basically what the Bell engineers did back when they were in 1955, when they're saying, all right, we're going to improve the quality of the line and how we're going to get better responses on the other side. A structured prompt that has the right set of information inside of it is the secret to be able to getting better answers and higher quality answers. Again, this is something that I think Shannon would find as intuitive. It's basically coding. It's engineering. You got to put the right bits together, and you don't have to be a coder to be able to do it, but you got to understand what it is that you're doing, how you're going to break that out, what the schema is, any semantic information that you can do. This is the reason why things like RAG matter. So, and now we're starting to add in more things. So you remember Theseus, that little mouse, electronic engineering robot mouse, in 1950. And it was an agent. It's trying to figure its way out through the world to be able to get from one thing to the other to the cheese, and then be able to remember it, and then have that sort of a persistent state that updates over time. What if we change the maze, right? In this particular case, the maze is small. In the world of today, the maze is huge. There's so many different things that could happen. So the architecture, though, is still recognizably the same. It is still the basic set of things that we bring together. Now, instead of running on lines in Shannon's basement or across the some barbed wire that he had to his friend's house, we're talking about transformers with millions of tools and access to the internet and all the different pieces that go through there to be able to actually enact work. So I want you to think about agents as a pipeline of pipelines. So on all those different pipelines that we had, we've got different ones that are thinking through different things. They're taking different actions, and they're following that full set of steps that was in our set of items. So when you start to inject different things like RAG and memory and permissions and humans are messy, you're not really just doing AI anymore. You're doing organizational engineering. And it's an important thing to think about, because that's how work really gets done. It's not just one atomic task and, we've automated this task and now we don't need whatever. There's a lot of other things that wrap around that. Now you can make it much more efficient. You maybe 10x it or higher, but that is not the only piece of the problem. And then there's different places where that noise actually happens, and we have to be able to engineer for that. So when Anthropic actually wrote some of the different bits inside of their engineering blog, their guide to building an effective agent. It says, and I do love this, like the most successful agentic systems are simple, composable, not ornate big frameworks. This is the same simple sort of idea that was back there in Bell Labs, and that simple way to be able to bring those things together. The more verifiable, the easier the set of steps, the better the output is actually going to be. Now, when I talk about organizational engineering, this is why. So agents don't just eliminate coordination problems. They industrialize them. This is like saying, okay, I've now added an army of smart interns, and I expect my company to be better. Why? That's not how it's going to work, right? So you've got to set up the ecosystem of things around it to be able to get the enable those interns to be able to do more. When you're talking about different agents, you may get different answers. What are you going to do about that? When you take all those different pipelines of pipelines and each one taking its own set of things, you have to figure out, okay, here's a different noise going in here, a different noise going out here, and here's how we're going to pull these different pieces together. You've got to pull those successful agents again into simple, composable patterns, not ornate frameworks. Same thing from the Bell Labs. And in order to do all that and make it as easy as possible, you got to have that paved road of things, right? You got to have that that set of governance. And if you're a leader, we were watching this, and whether you're a leader of people or a leader of bots, it doesn't matter. Thinking, okay, well, what's the actual job here? This is the job. This slide is the job, right? It is not just as paperwork, but as architecture. It's permissions, it's provenance, it's verifiability, it's visibility, it's all the audit trails that go along with that. It's what and where should there be human approval gates. If you think about NIST gives generative AI risk profile information, Microsoft Agent Docs, Anthropic, ChatGPT, all of them have different safety practices. They're rolling those different pieces together. They're all converging towards essentially the same picture from a governance point of view. And AI at scale is not just building a model, it's building a trust architecture that sits around all those different things of what can be done, by whom, with what evidence, how do you know it's correct, what were the permissions, what are the consequences, how do you measure that? This is Weaver's level C, effectiveness. It's conduct, it's action. It's, did I get the action that I expected from the message that I sent? So this is where we are right now, my opinion of where we are right now anyway. Did the symbols arrive? We're pretty good at that, right? Getting things done there, tokens at the speed of light. We're getting faster and faster on inference and everything else. Was it understood? We're getting better at that as well. This is moving along and moving along quickly. And then, but it's still got room. Memory is still a problem. Consistent memory across agents and different agent sessions. RAG is good, but only in certain situations, and it's not enough. So this is why there's so much work going on in fine tuning in memory and agentic memory and distributed system memory, etc. And then, did it actually change the conduct? Did it change the output that you were actually trying to do? How do you measure that? Right? What is the metric that you're looking at? Whether it's governance or permission, the oversight pieces, the right audit stuff, all of those types of things really need to be in place. And I think there's still a lot of work to do there. Shannon said this in 1956. Information theory has the last few years become something of a scientific bandwagon. It will be all too easy for somewhat artificial prosperity to collapse overnight when it is realized that the use of a few exciting words like information, entropy, redundancy do not solve all of our problems. Now just replace information theory with AI. Same problem, right? He warned us in 1956, and I think all of us are still doing this same thing. It is not a universal solvent to be able to use that model. It is the bottom of that stack. There's still a lot of other things to go through. We can staple all the words like entropy and redundancy and blah, blah, blah that we want on it. Going to come down to a number of other different things that humans are actually better at that will help to hold it all together as we work through the systems to be able to enact this at scale. So the meaning bottleneck is the significant one, right? So this is sort of the punchline of this particular thing. And we're not running out of information. There's lots of information. Every business has got its own set of things. And we have lots of well-meaning and meaning-making things. And machines are now producing more and more and more and more information and more symbols and more things that are coming at different people who are working within these different things, whether it's opinions, whether it's outputs, whether it's graphs, whether it's whatever. Every single meeting you go to, every news cycle, it's just overwhelming, right? Now, the bottleneck is not that stuff. It's the human deciding what matters. It is the human figuring out, okay, that was true or that was not true. I've in previous ChuckChats, I've talked about how your brain is essentially very lazy. If it sees stuff, it assumes it's right. And then later on, if it has more spare cycles, it will check it out and see whether it's true. These are fundamental facts that are causing an issue with this flood of information, this stream, this ongoing stream of information. So it is a moment that we're living in real time and something that we have to continue to work on. So in that bent, there are still a set of things that humans still own, right? We own truth tracking. Is it right? Is this real? We have to be able to build systems that will allow us to be able to do that, right? This is important trust building between one another within systems, right? It's not as simple as just saying, yeah, trust me. Judgment. Sometimes doing the right thing is harder, but it's still the right thing, right? The easy thing may not be right, but the math goes through. Accountability. Humans are still going to have to take accountability, right? How do you hold a set of code responsible for its actions when it takes something? It's going to be the human who acts that thing to do it that is going to be held accountable. And then care. I think this was important, right? It's bots can't care. They can't want the right thing for someone else just because it is the right thing. We as humans do this just naturally. It is built into who we are. So these are the things to think about when we're architecting our systems for the future and our organizations for the future. If you lead any AI rollout, if you're a CIO, a CTO, or you're just deeply involved in these things and trying to get it done, here's your checklist, right? This is the set of things that you got to be able to do. Figure it out, screen cap this, print this out, whatever. Keep the orange monster because he's really cool. It's not, the answer is not how big is the model. It's not which vendor is going to give you the answer that it is that you want. It's grounding, it's provenance, it's permissions, it's approval, it's the audit. How can you do all these different sorts of things? So get these right, and you start to move up the stack from Claude Shannon into Weaver's world. So he solved the problem on the wire. He solved to be able to move those different things through beautiful fashion. But the other Claude is still working on the meaning. We got to help, and we have a role in this too. So we got to be deliberate. We don't want to just, whether the Claude name is lore, it doesn't matter. The lineage is still real. The tie is still real. We have inherited that triumph over noise, but it still crashes hard, I think, on the problem of meaning. And the human factor is one where I think we still need to step up and step in. It's not bigger models that are going to solve the day. Actually, I'm of the opinion that we're going to get to smaller models that have the ability to learn. That's part of how we will be able to bridge that. I think there's going to be new architectures that are still coming. There's still a lot to do, a lot to learn, so many big things that are still coming. But we've got to look at all the things within that picture, and build meaning back in. If you thought this was cool and you want to read more, this is a set of books that you can go look at. I will do my best to put some links here in the chat for those who are interested in doing the follow-up and doing a read. But these are some of the different ones that I pulled different ideas from over time and throughout my own research for this. I would again like to thank Nicari2296 for the idea on this particular one. I loved this. This was beautiful. If you have ideas, if you're interested in me talking about something or doing a deep dive on something, by all means, send it my way. Drop it in a link. I look forward to it. I love falling into internet holes, as evidenced by this. But I'm Chuck DeVries. This was BrainCandy. If you liked it, send it to a friend who's been told or told you that AI is just autocomplete, and then see what they say. And I'll see you next time. I appreciate everybody's time. Hit the thumb up, hit that subscribe if you haven't, hit the bell so you know when I throw out more of this fun.